In the last lecture, we studied refraction from curved surfaces, which are separating media of refractive indices mu 1 and mu 2. And we derived this relation mu 2 by V minus mu 1 by U equal to mu 2 minus mu 1 by R, which is a relation between the image distance, object distance and the radius of curvature of the surface. And we found that this relation is the same whether the surface is convex towards medium mu 1 or it is concave towards medium mu 1. And we also see how images formed by such surfaces and how we can trace the rays. At the end, we introduced the basic forms of lenses, and we now continue from that point. This is a double convex lens, and you can see that it can be thought of as being made of several of these pieces, several of these prisms. And you can see that this prism, for example, refracts this ray and this goes this way, and similarly this one goes that way, and this one refracts slightly less than the other one. This one in the middle, which passes through a slab, does not get refracted at all. There is no change in its path. So, we find that in the middle of the lens there is a point through which a ray can pass undeviated. This point is called the optical center of the lens. Please be careful, optical center is not necessarily the center of the lens, geometrical center of the lens. It is any point in the lens through which a ray can pass undeviated. So, while dealing with lenses, we will have several terms like principal axis or optical axis and focal length, distance of the object, distance of the image and so on, and we shall be dealing with thin lenses. Thin lenses means lenses which are thin, whose width is very small compared with the focal length of the lens. Focal length we shall define more precisely, but you can understand the concept of focal length is the same as in the mirrors. So, we shall assume that the width or the distance between two surfaces of a lens is small, very small compared with the focal length. Such lenses are known as thin lenses, and we shall work in the context of thin lenses. And we shall also take only paraxial rays. Let me remind you, paraxial rays are rays which are near the axis, and they make small angles when they strike the surface of a lens or a mirror. And optical center we have already defined, and let me remind you again, we shall be using Cartesian convention for signs. And here is what all this means. Instead of taking this lens like this, we shall in some diagrams be taking just a line showing that the lenses are very thin, and this is a point inside the lens through which the ray goes undeviated. This is called the optical center of the lens. You can see this is not necessarily in the middle of the lens, and in this diagram we will show it just like this, and this line going through the optical center is called the principal axis of the lens. We are now considering first of all the convex lenses. A convex lens is one whose surfaces are convex, either one or both, or convex towards the medium outside. Okay. So, we will take the convex lens, and for a convex lens, if the rays are parallel to the principal axis and are paraxial, although they do not appear to be paraxial here, but keep this in your mind that the rays we are considering are always paraxial, and these rays after going through the lens meet at the point F, and therefore, F is called the focus of the lens, and the distance OF is called the focal length. All distances are measured from the optical center. So, this is the focal length of the lens, and by our convention distance measured in the direction of light OF is positive. So, the focal length of a convex lens is positive. If the rays are inclined to the principal axis, they still meet in the focal plane, not at the focal point, but in the focal plane. And once again, the let me remind you that the focal length of a convex lens by our convention is positive. The rays emanating from the focus, they become parallel after going through the lens, after passing through the lens, after refraction through the lens, they become parallel to the axis. And similarly, rays emanating from a point in the focal plane also, they become parallel to each other, but not necessarily parallel to the axis. This is another way of understanding the functioning of a lens. You see, this is the focal point and the rays from this after going through the lens become parallel. That means that spherical wave fronts, they become plane wave fronts after the light passes through the lens. Similarly, plane wave fronts, they become spherical wave fronts when the light passes through the lens. I am not sure if you are familiar with wave fronts, but we shall study them later on, these wave fronts. Now, let us take a concave lens. This is a double concave lens. What happens here? The lines, the rays which come parallel to the axis, they diverge. That is why this lens is known as a diverging lens. The convex lens is known as a converging lens, and this concave lens is known as a diverging lens because the rays diverge and they appear to come from this point F. So, this OF is the focal length of the concave lens, and you can see from our convention that this OF is negative. So, the focal length of a concave lens is negative. To find how the image is formed by the two surfaces, let us see the role of each surface one by one. We have this object at A, this is the ray OQ, it meets the first surface, gets refracted, and if the second surface were not there, then this would go to I1. But since this second surface is there, it suffers another refraction and comes to I. We can say that for the second surface, I1 acts as the virtual object and I is the image formed by the second surface. So, this is how we understand the image formation by a lens. A ray like AQ strikes the first spherical surface at Q, where it is refracted in the direction QS in accordance with the laws of refraction. If there were no second spherical surface, this would meet at I1, as I have been saying. However, at S it suffers another refraction and goes to I, and I1 can be considered as the virtual object for the second surface. And the distance from O of A is U, the object distance. Distance of I from O is V, the image distance. Okay? And keep that in mind. Let us break the process of image formation by a convex lens into two parts, one part on this surface, another part on that surface. So, the first part is refraction at the first surface. So, this ray gets refracted to this, goes to I1. R1 is the radius of curvature of this surface. Phi is this angle, alpha is that angle. As before, we have been doing this many times now. So, you must be familiar. Mu 1 is the refractive index outside and mu 2 is the refractive index of the medium inside the lens. And we have derived this relation, if you remember, mu 1 by V. In this case, V is V1, because we are going to use another surface where this would be the virtual object for that surface. So, we use the name V1. So, mu 2 by V1 minus mu 1 by U is equal to mu 2 minus mu 1 by R1. R1 is the radius of curvature of this surface. What happens in the second surface? We have this ray QS would have gone to I1, but because of refraction it goes to I. So, I1 is the virtual object for this surface, that is V1 is the virtual object for this surface, and the actual image is formed at I. So, therefore, V is the actual distance of the image from the surface. R2 is the radius of curvature of this surface. Mu 2 is the refractive index inside and mu 1 is the refractive index outside. So, you can see what happens. We have taken refraction at this surface first and then at this surface second time. And again we have the relation mu 1 I equal to mu 1 R as before, and angle I is alpha plus beta, and angle R is equal to beta plus gamma. So, we substitute these values in terms of the distances assuming small angles, then we get mu 2 by 1 by V 1 plus mu 2 into 1 by R 2 equal to mu 1 into 1 by R 2 plus 1 by V. And if we apply the sign convention, then it becomes mu 2 by V 1 minus mu 2 by V, mu 1 by V equal to mu 2 minus mu 1 by R 2. This is the relation for the second surface. So, we can add the two and we get this relation 1 by V minus 1 by U is equal to mu 2 minus mu 1 by mu 1, and this gives us 1 by R 1 minus 1 by R 2. This is known as Lensmaker's formula, and this we got by using this equation and this equation which we have derived earlier. So, from these two equations we get the relation 1 by V minus 1 by U is equal to mu 2 minus mu 1 by mu 1 into 1 by R 1 minus 1 by R 2. R 1 and R 2 are the radii of curvature of the two surfaces. Mu 1 is the medium outside the lens, mu 2 is the medium inside the lens. If medium inside the lens is mu and medium outside is air whose refractive index is 1, then it simply becomes mu minus 1 into 1 by R 1 minus 1 by R 2. This is known as Lensmaker's formula. Why? Because a lens maker has to grind the lens for a given focal length. So, he must know what the two radii of curvature should be given the refractive indices and so on. So, this is known as Lensmaker's formula, and 1 by V minus 1 by U is 1 by F. So, 1 by F is equal to this mu 2 minus mu 1 by mu 1 into 1 by R 1 minus 1 by R 2, and this we can get easily. You see, if we take the object to infinity, this becomes 0. So, this becomes 1 by F. So, 1 by F is this, and therefore, 1 by V minus 1 by U is equal to 1 by F. We shall use that later as the lens equation, but from this equation by taking U to go to infinity, so that V becomes F, we get 1 by F is equal to this, and this is the lens formula, that is the Lensmaker's formula, which is in terms of the radii of curvature and refractive indices, and this is the lens formula in terms of V U and F. In applying this, of course, we shall have to use proper signs for V, U and F in accordance with our convention, Cartesian convention. Now, if the focal length of a lens is expressed in meters, then 1 by F is called the power of the lens. For example, if the focal length of the lens is, let us say, 10 centimeters, that is its 0.1 meter, its power is therefore 1 by F, 1 by 0.1, that is 10, and the unit for power is diopters. So, it is 10 diopters. If the focal length is 20, then that is 20 by 100 meters, that is 0.2 meters, then the power is 5 diopters. If the focal length is 100 centimeters, then power is 1 diopter. So, power is 1 by F, where F is expressed in meters. That is the power that your optician uses for making glasses. And if the focal length is negative, as in the case of a concave lens, then the power is negative. It is 1 by F expressed F when F is expressed in meters, and the sign it carries, whether positive or negative. All right, let us look at the ray diagrams for lenses. This is the object here, and in fact, we can draw many rays, infinite rays from this. but as we shall see only 2 would suffice. But let us take the tip. From the tip we draw a ray through f, and after passing through the lens this becomes parallel to the principal axis. From the tip we draw a ray parallel to the axis which must pass through the focus on the other side, and we can draw a ray through the optical center, and this ray is not deviated. Wherever these 3 rays meet, that is the image of this point. So, this tip is the image of this tip here. As you can see, we do not need actually 3 rays, we can draw any 2 rays, and wherever they meet in the case of convex lens or where they appear to meet, that is the image of the object. If the image is inverted, it is a real image. If the image is erect, we shall see that is a virtual image. You see, as I have been saying, we can draw infinite rays through all these points which pass through the lens. So, even if a part of the lens is blocked, we still have rays which pass through the unblocked part and form the image. So, if a lens is broken, for example, half of it is broken, does not matter, we can still form an image. This will still act as a lens. The only difference would be the image would not be as bright as it is with the full lens. Why? Because some of the rays have been cut off from reaching this point, and therefore, some of the light that would have gone to this point cannot go because the lens is blocked or broken. Therefore, the image is fainter than the image formed by a complete lens, but it can still function as a lens. Now, let us take the case where the rays appear to meet. In the case of convex lens, let us say this. What happens? We have an object between O and F. O is optical center, F is the focus point, and 2 F is twice the focal length. So, we take 2 rays, one going through F, which is undeviated. So, it goes like this, one parallel to the principal axis which must go through the focus on the other side. So, these are the 2 rays. These 2 rays are diverging, they will not meet on this side, but when they are taken backwards, when they are extended backwards, they would meet at this point. So, therefore, this tip is the image of this tip, and this foot is the image of this foot. Therefore, this is the image of this object. You can see that the rays appear to meet, they do not meet. Therefore, this is a virtual image, and this is erect, and this is magnified. Now, let us see how the image changes position when object is moved this way or that way. When the object is at infinity, the image is formed at f. When the object is between 2 f and infinity, you can see by drawing the ray diagrams that image is formed between f and 2 f. When the object is exactly at 2 f, the image is also formed exactly at 2 f, and in this case as well as this case as well as this case, the images are real. They can be obtained on a screen. There the rays actually meet. We will continue with this study in the next lecture, and we shall use, and we shall in fact do many examples also of the lens formula 1 by v minus 1 by u equal to 1 by f, which we shall redraw in fact by some other considerations. Here you remember we drew this formula, derived this formula how by considering refraction at this surface and refraction at this surfaces. Now, we shall take the lens to be a thin device and see by trigonometrical means, by comparing triangles and so on, we shall find this relation once again. And we shall also show that if 2 lenses are placed next to each other, then the focal length of the combination is equal to 1 by f 1 plus 1 by f 2. In your spectacles, these lenses are almost touching the eye lens, they are in contact, and therefore, the focal length, the power, you can see the powers are added. This is power, this is power, this is power, these powers are added. So, the powers of the 2 lenses, this lens and the lens of the eye, they get added. And we shall also see the devices like telescopes and microscopes.